Okay, so hello everybody, thank you for coming. I guess most people in this room know about or have at least heard some things about free software and how successful it is today. And when you compare it to what the industry is doing, I think it's pretty obvious that Linux is a very successful operating system compared to, let's say, Microsoft Windows, which BSODs on ATMs, which is quite funny. But when you look at what's available in the hardware world, most hackers play with basically microcontrollers and LED blinky stuff, nothing really advanced. And when you compare that to what the industry is doing, well, it's pretty obvious to me that there is a big elephant in the room, and that all open source hardware projects are nowhere near doing any sort of this chip design. Now, obviously, you don't need such an advanced factory to design a chip at all. This factory is for making chips by the million. But still, I still think we have a problem with hardware in the hacker community. So, to address this problem, 5 years ago, I started a project called Milkymist, which is what I'm going to talk today about. And Milkymist develops, for starters, it develops an open source system on chip design. So what I mean with a system on chip is a set of peripherals which is integrated in one chip, which contains a CPU core, and then lots of peripherals all around. That's typically what you have in a mobile phone, for example. In a mobile phone, you will have a CPU, which is typically an ARM device, and the CPU connects to all sorts of stuff like a UART or a GSM baseband processor, or a SIM card controller, memory, SDRAM controller. That's also what you have in boards like the Beagle board, for example. You have one chip on it, which implements all the functionality of the Beagle board. I think everyone knows about the Beagle board, right? Or yeah, okay. So yeah, that's basically one chip which does everything. And in this chip, you have the CPU and integrated buses and some peripherals. Basically, it's a computer on a chip. When you have a computer like that, you have the CPU with a discrete chip made by Intel, typically, still these days, unfortunately, because x86 is not the best instruction set in the world. And you have a PCI bus and then peripherals, which these days they tend to be grouped into one Northbridge and Southbridge chips. But still, they are more like discrete chips. And system on chip is everything in one chip. That's basically what is used in embedded devices like iPad, iPhones, everything I mentioned. So one of the goals of this Milkymist project was to develop such a system on chip using open source design techniques. So that means all the design files for this nice system are available under the GPL license, are actually available today, they work. And what do we have in here? So we have a little overview of the system. We have the CPU here. It's a Mico 32 CPU. That's actually the only part that we didn't develop in this project. It's a CPU core which was made by the Lattice Semiconductor for use in their FPGAs. And they have released it under an open source license, which resembles the BSD license, but it's not exactly BSD license. And using this CPU core as a base, which makes approximately 20% of the lines of code of the complete Milkymist system, we have built this complete design, which includes a memory controller for NOR, for SDRAM. It includes basic peripherals like you have USB, you have a serial port, you have GPIO, basically what you expect of a microcontroller. And then you have more specialized peripherals, like, for example, an audio controller, infrared, integrated MIDI, integrated DMX. The DMX is a protocol for controlling stage lights. And I'll get back to that a bit later, why we have such weird stuff integrated in the system on chip. We also have a video input controller that takes BT656 video. It's a digital video format which is used by chips which digitize PAL or SECAM analog SD video and do all the nasty processing and put out a better signal which is easier to process. It's a standard. Okay, so we have some computation acceleration here as well. These two guys here are, yes? Sorry? Yeah, NTSC worked as well, but actually the BT656 standard is transparent to these standards. The decoding between NTSC or PAL or SECAM is happening before the BT656, and then it doesn't really matter if you have PAL, SECAM, or NTSC. There are some differences because the refresh rate is not the same, but the basic BT656 protocol is exactly the same. With just small difference in timings that is very easy to take care of. You don't have to do all this messy signal processing yourself with all the legacy. Well, signal processing is interesting, but really PAL, SECAM, and TSC is there's really a lot of legacy, and if you want to accept signals coming from all sorts of sources, which can have some noise, which can have some other distortion, which can be interlaced or not interlaced, it's really a mess. So it's pretty nice to have a little chip which takes care of this little legacy mess for us. That's why we didn't want to develop this part as open source, even though it would be a relevant thing to do. So so except than a processor and I/O peripherals, we have some accelerators. We have an accelerator here called the PFPU, Programmable Floating Point Unit. It's basically something which is analogous to a vertex shader that you have in graphics cards. So what it does is you put a set of equations and it evaluates them very fast. And TMU is basically a graphics pipeline. It's a 2D graphics pipeline with some other restriction. It means texture mapping unit. It is a bit more than texture mapping, but that's basically when you are drawing some polygons in OpenGL, and then your graphics card takes care of it, and the TMU implements a subset of OpenGL. So we developed all this as an open source licensed system on chip, and now comes the question, how do you do such a thing? Well, it's just basically just logic design. I think this might be something that you know about, Nixie clock. It's a very popular project for people who do electronics. And this Nixie clock is actually not using a microcontroller. A lot of people these days use AVRs for Nixie clocks because AVRs have become really cheap and very powerful. But this one, particular one, didn't use any microcontroller. Instead of using microcontrollers, it uses basic logic gates, which you see here. They are CMOS or TTL logic gates. And all the functionality of the Nixie clock is just implemented with logic gates and flip-flops. So when you take that to the next level, you can build actually complete CPUs with that. So that's actually a CPU built with TTL logic gates. As you can see, it's pretty heavy. And when you look what's inside, it's an even bigger mess. You see with all these wires and all that stuff. So when you are designing this, what you have to do is pick chips manually. You need to think about the functionality of your CPU. Then you have to decide what sort of TTL chips or CMOS chips that you want to use. CMOS chips come with various sets of logic gates, so you need to optimize. One chip can use different functionality of the CPU because let's say you have a chip which has 8 AND gates in it, and of course you want to distribute these AND gates in different parts of the CPU, so you have to do that manually. Then you have to find a layout for the chips, and then you have to connect all the wires together, and it creates one big mess like that. So if we were to design the Milkymist system on chip using such technique, which is possible, it would really require a lot of manual work. It would probably be a machine which is the size of this table, and it would be pretty slow because you have all these delays over routing in the different wires. So to address the first problems, modern chips and modern logic designs use what is called hardware description languages. So there is VHDL or Verilog. They are the most prevalent languages these days. And what you would do is describe the behavior of your logic using a simple algorithmic description. Like, for example, you can have variables, and then you can assign a logic equation to that variable. You can have conditionals, and when you put that into the software, it will process all the conditionals and logic equations into whatever you want. Actually, it can be TTL chips. It is theoretically possible to develop a synthesizer which automatically partitions and selects TTL chips for you. But typically, when you have a logic design which requires VHDL or Verilog, TTL chips are way too small for implementing such designs. So instead of having TTL chips, you just have what is on the chip of the TTL chip. That is what is called the standard cell in ASIC designs. It's basically a pre-made pre-made semiconductor layout for, let's say, a D flip-flop or an AND gate or anything, and the synthesizer can pick up the correct gates from all this pre-made library and use them to implement your behavior that you have written using VHDL or Verilog. And so that's for making actual chips. But when you are using an FPGA, FPGAs use lookup tables instead of standard cells. So lookup table is just a black box which can implement any, let's say, 4 or 6 input logic function with one output. And the synthesizer will partition your big logic design into smaller lookup tables, which can later be programmed into an FPGA. And after your design has been converted into this set of standard cells or lookup tables, then comes the step of the placement. The step of placement is very similar to doing it's just like placing the logic gate when you are doing this homebrew CPU. You have this breadboard and you need to place the chips at the right position. Of course, if 2 chips are communicating together very closely, you need to put them very close to one another. And it's exactly the same problem when you are designing a chip or an FPGA. When 2 standard cells or 2 lookup tables are communicating together, it's a good idea to place them together, to place them close, so you don't have a lot of wiring and a lot of delays all over the chip. And the good thing is there are tools which do that more or less automatically. And when you are using this synthesis flow, that's something which is, I would say, 99 or maybe 99.99% of the placement is done automatically using a software tool, which, it's actually not too complicated to develop such a tool. A lot of people think it's impossible. I don't think so. First, because companies have done it, obviously, and I don't think open source developers are more stupid than engineers in companies. And the techniques used are based on, it's basically an optimization technique. So you can use things like simulated annealing or some other heuristics based on function analysis to develop an algorithm which gives a placement which is good enough and meets a set of constraints. So once you have placed your different logic gates on the surface of your chip, you need to connect them together. And that also is done automatically. When you have a chip, you need to draw metal bonds to connect all the pins of your logic gate together. And when you have an FPGA you can route signals in an FPGA using what is called PIPs, which means programmable interconnect point. There are little programmable switches inside the FPGA chip, which connect 2 pre-made wires together. So it's like the old school phone networks when you have people connecting with jacks to different lines. It works exactly the same. You enable switches in the FPGA and you route all the signals through all the pre-made lines. That's just basically how it works. It's actually not something which is very complicated. It's just like designing a Nixie clock, but on a larger scale and with better tools. And as you might have noticed, the Milkymist chip has lots of funny interfaces and it has some graphics acceleration. Why do we have that? Because one of the things we are developing is actually a video synthesizer. It's a device which you see here. You can take a performer or dancer, any sort of object, you film them, and it gets into the device and gets synthesized into all sorts of effects that you can program yourself. Then you can control that with MIDI or DMX or whatever, or even OSC over Ethernet, and that's why you have all this stuff which is integrated into our FPGA. So, what have we done in 5 years? Well, we have actually designed the system on chip, which is implemented in the FPGA you see here. We have designed a PCB layout for it, so we are manufacturing our own PCB. We have mechanical layout. Well, basically, we have a finished product. We have some people manufacturing it. You can buy it online. It works. You can hook it up. Actually, some VJs are using it. So this video here was made with this little device. It was made live from this experimental 8-bit music you've heard. Yeah, we don't have actually very good videos. That's one weak point that we have. We only have this small screen and stuff. Hopefully someday we will shoot good videos. I hope. But yeah, people are actually using this stuff and they can use it. This guy is actually not a computer programmer. Well, he has some programming skill, but he's not a professional programmer. And he still managed to use it. If you look at Milkymist from an open source project perspective, we have 15 active developers. And if you want to put that into some perspective, I can refer you to this talk by Benjamin McCaughey, which is entitled When Free Software Isn't Better. And it's actually a very interesting talk. And one of the points that he makes is that most open source projects are not as collaborative as most people think. If you look at the breakdown of all source software projects by number of developers, you can see that the vast majority of projects have exactly one developer. And if you look at 2 developers, it's already a lot less, and the more you go, it drops down to 0 very fast. And the Milkymist project is here. So I think it has been pretty difficult actually to get here, but we've made it, and the project is pretty active now. We have people doing very interesting things with it, like, for example, people are porting the LLVM compiler to the Mico32 architecture that we used in the first place. Right now we are using the GCC compiler, which has a number of problems. And now we have an experimental LLVM port. We have people doing, what are they doing? Someone contributed a QEMU port. So when you want to develop software on the Milkymist, you can develop it on your computer and emulate it with QEMU. It will emulate the complete system, and it will even forward the graphics acceleration operation to your GPU. What else do we have? We have people working on the MMU for the Mico32 processor. Right now it's a simple processor without a memory management unit. So you cannot basically do a lot of things which are nice to do with modern operating systems. And someone is working on that now. We have people working on a Linux port. So right now it's UC Linux, which is a Linux version which doesn't require a MMU. But it's working today actually. You can boot a Linux on the platform, including the frame buffer, the keyboard, all the stuff. It's a completely working Linux system. We even have the OpenWRT distribution and build system to make it easier to develop stuff on the Milkymist. It's working except that it has no MMU. And hopefully this will be addressed in the near future. Right now this device doesn't use Linux, it uses an operating system called RTEMS, which was initially developed for the US military. The acronym initially stood for Real-Time Executive for Missile Systems. And it has become open source, I think, in 1995 or something like that. And now its missile was replaced by multiprocessors. And now it's being used in all sorts of other projects. What else people are doing? Yeah, we have some USB on it. And the USB is entirely controlled by the FPGA. Right now it's USB host ports, and someone is having fun trying to convert that into slave ports. You can do that because you can just program the FPGA and do whatever you want with it. All the USB signal processing is done inside the FPGA. On the PCB you have only analog transceivers to adapt the signal levels, and then all the sampling and the signal generation is done by using the FPGA matrix. So it's a very flexible architecture. Yes? It's Xilinx, it's Spartan 6. But the code is portable. I would say the vast majority of the code is entirely portable. So the buses we are using the Wishbone bus, which is around the CPU. We're using Wishbone, and then we have 2 custom buses that I have developed specifically for this project. Basically, we did not want to use Wishbone for the main area where we didn't want to use Wishbone was for the DDR-SDRAM controller, because this processing video requires a lot of memory bandwidth, and Wishbone doesn't, at that time when I started the project, Wishbone didn't support pipelining. Now it does support some pipelining, but it's pretty hard to use. And since I wanted pipelining and bursts as well, I just developed my own bus which supported both of these optimization to have better memory boundaries out of DDR SDRAM chips. Yeah, I am. It's DDR1, by the way. Well, right now, but we are going to switch to DDR3 in a few, probably in 1 year or something. DDR3 is pretty hard because you have a very high clock rate. You have a lot of serialization between the DRAM core and the I/O frequency, and the current architecture cannot really deal with that very well. I'm going to talk about this very briefly later, but I am in the process of completely refactoring the system on chip, and it will be possible to run the DDR at a multiple of the system clock frequency with the next version of the system on chip, including and the memory controller will be able to reorder transactions and also issue several commands to the DDR into one single clock cycle by just running multiple state machines in parallel, each taking care of one of the DRAM banks. I don't know if it makes sense to you because I don't know. Do you know about DRAM or? Okay. And have you touched some DRAM already or?
Yeah.
Okay. So you know what I'm talking about banks and stuff like that. Okay. Okay, so what was I saying? Yes, another contribution we got was URGTAG support for our FPGA. Actually, there are some other people using URGTAG to program FPGAs. Actually, this complete FPGA support into URGTAG was initially developed by one of our developers. We also have a little GTAG board. So it's a hardware contribution that's interesting. But I don't know if you have used the Xilinx GTAG tool already. Okay. I don't really know what the Altera tool is worth, but the Xilinx tool is horrible. It's very slow and proprietary. It takes several gigabytes. And instead of that, we have URGTAG and our own small cable. Yeah, you have a question or any question?
Yeah.
A VHDL simulator? Our code is very log, so we don't have any VHDL yet. But why? Of course, we have a lot of simulation because developing such a system on chip requires lots of code, and you cannot just download it into the FPGA, and when it doesn't work, you don't have any visibility on it. So of course, we need to run a lot of simulation, a lot of test benches, in order to fix all the bugs before they reach the FPGA. Because once they are in the FPGA, you cannot observe any signal which is inside the chip. Well, you can, but it's very difficult. So if you don't simulate it, you don't have visibility on your design, and you cannot fix bugs. We use Icarus Verilog. It's an open source simulator. Icarus Verilog. So it's a mix of, we use Icarus Verilog and GPL Seaver. It's also an open source simulator. Yeah, Icarus, yeah. Okay, so what was I saying? Yeah, we haven't got some of our developments, some of our IP, as some people say in the industry. I don't really like this word IP. I would say logic core because IP means intellectual property. It sounds like something which comes from the mouth of a lawyer and not an engineer. And so I prefer to use the term logic core or gateware. So we got some of our logic cores into pretty interesting projects, like for example, the Electra software-defined radio. You see it, it's in this little box here. And it's an experiment by the NASA to develop a new communication systems, which is going to be put on the ISS in July this year, and probably on the Mars orbiter, but that's less certain, which is going to be launched in 2014. So they are using actually the DRAM controller that you mentioned earlier. Not the one which has serialization, the current one. So now I'm going to talk about what we are going to do next into this project. Because even though it's a pretty nice project already, it still has a lot of limitation and it can be improved a lot. I would say it's probably just the beginning of a lot of things. So one of the first things we are going to develop is the mid-gen system. Right now we are using Verilog, and Verilog is not very good to develop complex designs like this next generation memory controller. So we are going to use Python to develop the next version of the system on chip. So MyGen is a Python library which makes it possible to apply modern software concepts such as object-oriented and meta-programming to design hardware. So this enables more automation. You can make your designs more flexible, more parameterizable. And then you have a host of libraries to build from a higher level description, banks of configuration and status register, interrupt controllers. So for example, you are just able, using a mid-gen system, you can just give a list of signals which should be treated as interrupt sources, and then it will automatically connect this interrupt to the CPU, and then generate registers for enabling the interrupt, querying status of the interrupt, or masking the interrupt entirely automatically. You don't have to type all the code to generate that register automatically. It can generate bus interconnect automatically as well. Right now, if you have several peripherals to connect to the wishbone bus, for example, using Verilog or VHDL, it's really a pain. You need a lot of manual coding. There are some tricks in VHDL, they don't work in Verilog, but there are some tricks in VHDL using functions to be able to build flexible interconnect using functions and record arrays. You can do that in VHDL, you cannot in Verilog, but either way it's a mess. And when you are using Midgen, all you have to do is you are using the object-oriented capabilities to you just have to give a list of bus objects that you want as masters on your bus. You give a list of slave objects, and you're done. It automatically interconnects the complete stuff. And another area which we are working at the moment on Midgen is synthesis of data flow systems. So data flow system is basically a graph of actors. An actor is something which performs an operation like multiplication or anything more complex. It can be anything. It can even be something which accesses system memory. And you would give this data flow description of an algorithm, and Midgen will be able to develop automatically some other implementation of it. That's something which is work in progress now. It doesn't work so well today. There is some code which does it, but it doesn't do it well. And it's more like blue skies research today. And Midgen is actually something that we develop in collaboration with the Rhino platform project. It's a project from the University of Cape Town in South Africa. It is basically a platform for doing software-defined radio. So you see here there is an FPGA, it's a Spartan 6 LX150, which it has an AVR processor, an ARM system on chip. And the ARM system on chip runs Linux, and then it communicates with the FPGA, and the FPGA can implement interfaces to go to the ADCs that you see here. And it can also implement some hardware acceleration to process the signals, and that's where they're going to use this Midgen data flow system to generate more easily the hardware accelerator for the radar processing, for the radar signal processing elements. And yeah, it has a lot of fancy stuff like Ethernet, USB, well, all the stuff which comes with the ARM system on chip, basically. So, another field of possible application for the Milkymist system on chip is this little cute laptop. How many of you have heard of it, by the way, of the NanoNode? One person? No one else? Okay. So actually, the NanoNode is this little small laptop. It's really the size of a cone of Coke. And it's manufactured by the same people who manufactured the Milkymist. Right now, it is based on a proprietary system on chip using a MIPS CPU. And we are thinking about switching it to the Milkymist system on chip design, maybe after the MMU is done, so it can run fully fledged Linux. And this might mean that we are going to switch from FPGA to ASIC. So I would say economically, it might not make a lot of sense to switch to ASIC because that's still a small product. So it's going to be more expensive, definitely, but ASIC still remain pretty affordable. You can have a small series for like $10,000, something like that. So it's going to be more expensive than Genic, but it's also a learning experience, and I think some people, some free software advocates, or some people who are interested in playing with architecture are probably going to be willing to pay a bit more to have this free system on chip. I'm not saying we are going to sell a lot, and it's going to be relatively more expensive, but if you want to learn about chip design, I think it's a great project to do anyway. And this brings me to the next Milkymist video synthesizer, what we are going to do next for the main Milkymist video product. Well, we are going to basically do what everyone is doing these days, just increase resolution, have more video outputs. Well, pretty boring stuff, everyone's doing that, but everyone wants that at the same time. We are going to use what I talked about earlier, this Midgen synthesis system in Python to build the complete system on chip. Maybe we are going to switch to ASIC as well, but not entirely sure. Because what I like as well as a Milkymist video synthesizer, it is a very experimental product. People can do whatever they want with the FPGA, change the complete design, and we would lose that if we switch to ASIC. And well, or maybe we can just have two chips. If we switch the NanoNode to the Milkymist system on chip, we can have the CPU in one chip and the FPGA doing the rest. And this actually brings a lot of performance advantage because FPGAs have one big problem, is they are very inefficient. These days, when you have a mobile phone which runs at 100 gigahertz, it's not because they have made such a good design in VHDL or Verilog, and we have made a bad design because it runs only at 80 megahertz in the Milkymist. It's because FPGAs are just extremely slow compared to ASIC technologies. In your mobile phone, you have directly, let's say, 28 nanometer transistors, and these are really fast compared to a slow FPGA like we have in here. And that's what makes the difference between 1 gigahertz and 80 megahertz in the Milkymist. Actually, I did try implementing the CPU core in the Milkymist into an ASIC process and then run a timing analyzer on it. Because actually, you can also determine the running frequency of your design using software techniques. So you don't need to build the chip and try how fast it runs. There are models which predict that. And I tried to do it for the Milkymist design. And if you use 90 nanometer technology, which is already pretty old these days, it runs at 800 megahertz. So it's definitely not a problem with the Verilog design. It's just a problem that FPGAs are stupidly slow. And another area of interest that we are going to explore is really the user interface. These days, the user interface of the Milkymist is, well, I don't know, I wouldn't call it bad, but I would call it mediocre. Especially because you have to switch between programming mode and visualization mode. And a lot of people don't get that or don't like experimenting, switching values and then switching between modes. It's pretty difficult for a lot of people to comprehend, which is understandable. So we really want this product to be usable by everyone and unleash their creativities. So we are going to make a lot of effort in the near future developing what is called a tangible user interface. So what I mean, I find this project pretty inspiring, the React table. It's one table, you will see it in the video. You put object on the table and it makes sounds. You have the idea. So I pretty much like this project with this user interface based on just physical interaction. And I'm thinking about doing a bit the same, but with video. And I would also like to, this design is actually very bulky. because it works with a video projector which is under a table. It's approximately this size, in fact. And you have a video projector under the table, which projects this image that you see. And the objects are detected because they have a little symbol on them. And there is infrared lighting under the table as well. And then a webcam just processes the image. It's very simple. But the problem is that it's extremely bulky, so you cannot really transport it. It's pretty bad for that. And I would like to develop something like that, but using radio frequency instead of infrared. And that would probably make it possible to make a small tablet, which is also interactive in this way. And I would do it probably by using the same principle as Wacom tablets, which is sending a signal like RFID into a pen or some smart object, and then sensing the return signal using a grid of printed codes on a PCB, and determining the peak of the signal, which gives the position of the object. And so it has two advantages. First, it can be made into a tablet which is this thick and not a big table like that. And the second advantage is the objects can be smart. Here you only have a piece of plastic with a symbol on it, and it cannot interact or anything. If we use radio frequency, we can add buttons, we can add gyros, accelerometers, all sorts of stuff that we want into the objects. So it opens a lot more possibilities than just a rectangle. Right, so if you want to learn more about this project, feel free to come to our IRC channel, Milkymist on Freenode. There are always people on it. If you have any technical questions or anything, go to the channel or just ask me. I will be in the room later. We have a mailing list, of course, and you can follow us on Twitter. And before the demonstration, I would just like to advertise a little bit a conference that I am organizing in Berlin, in Germany. I know Germany is pretty far from here. I come from there, so I know it far. But EHSM, Exceptionally Hard and Soft meeting, is going to be in December 20 to 30. And it's about the most hardcore DIY and open source hardware and software that you can find. Like people building particle accelerators, cyclotrons, let's say vacuum tubes. There are actually people who are trying to build chips. I mentioned chip design at the beginning. And there are actually people who are working on that. They are going to be invited to this conference too. We have people, we are going to have tons of stuff. Actually, we haven't made the program yet. We have just managed to book the rooms like 2 days ago. That's why I'm just announcing it now, and you will not find anything on the website yet. But if you follow us on Twitter, you will be able to get updated when we get really public about this event. So I think if you don't have any questions, I can plug this thing, and you will see what it's doing. Yep. We are using the Lattice Mico32 CPU core, which wasn't designed by us. But all the rest, it was custom designs, because there is some stuff on opencores.org, but most of it is extremely buggy and extremely bloated, so we tried using some and it didn't work. It was basically a waste of time, because I tried using it and I just figured out that it was completely buggy and broken by design, so I ended up regretting everything. In a lot of cases, I haven't really benefited from opencores.org. Sorry? Yes. Yep. No, it's actually a BSD style license. Well, if you look at in the strictest sense of the free software license, you could say it's not open source, not because Lattice wanted to close it down, but because the Lattice license has this stupid US export restriction on it. And because of that, it contradicts the open source spirit. But that's the only problem that we have with the Lattice Mico license. Yes? With what? The Altera? How do you call it? Acronics. Acronics, no, we are not. Actually, Acronics FPGAs are extremely expensive, and they're definitely not for this market. They are used in telecommunication appliances. And one Acronics chip is several $1,000s. And I don't actually know how fast they run, because Acronics is a quite secretive company compared to Xilinx or Altera, where you can just download their stuff and try it for yourself. And I don't even know if the Acronics claims are true, because I have never seen them in action. Sorry? Yeah, but you see lots of stuff in advertisement. Yeah. Oh, yeah. I have another presentation about that I gave in October, and I don't think we have time, but if you want, I can go to the breakout room if you have a video projector. Do you have a video projector in the breakout room? No? Okay. Anyway, today there are no free software to develop this, but I think it is totally possible to develop it and reverse engineer the bitstream format. And yeah, if you look at I think I have a few slides. I can show you a few slides maybe. Actually, they do publish a lot. Let me just find it again. They do publish a lot. Yeah, what is that? No, that's not the right one. Ah, yeah. So if you look at for this presentation that I made, so that was a presentation that I made in October about building open source FPGA synthesis tools. And actually, if you look at the bitstream format, you can find a lot of documentation which is published by the FPGA vendors, which a lot of people are surprised to learn about that. But you can find for example, a complete list of the pips, which are programmable interconnect points from the Xilinx chips, just by running the tools with the right options. And if you look at how it's encoded in the bitstream, so yeah, that would be a pip, for example. It's just a pass transistor, which would connect this thing with this wire here, with the output when it's switched on. And when you look at how it's done in the bitstream, basically it's just a group of 2 bits that you see here. So you switch on this transistor just by setting the bit to 1, very simple, and you set the other transistor here just to switch it on as well. And this connects this to this. And if you want to know where this is connected, to which slot is connected, you can also find that in the documentation from the FPGA vendors. So it's actually not a big obstacle that FPGA vendors are not documenting a lot of details of the bitstream message. It's just a problem of people being lazy. Yep. To do what? Yeah, that's what my journey is about. Well, at least the data flow part. The data flow systems are inherently parallel. Yeah.
So right now, the
actually, we are able to run the user interface in 1024 times 7600. Yeah. And it doesn't work in rendering mode yet because of memory bandwidth problems that I'm going to address in the next version of the system on chip.
Yeah, and for your next version, go ahead and finish the first part.
You have some. Oh, actually, you can do it. No, it works as well without the transceivers. This Spartan 6 chip we are using today is capable of doing HDMI and DVI, and in the very next specific version, which is actually being manufactured now, it's being routed actually at the moment. We are going to have replace VGA with DVI, and you will have DVI-D. So it is possible to do it with minor changes to the current design.
So you don't need to higher end.
No. They are not more expensive anyway. Okay. No further questions? I can plug it in. Okay. Actually, there might be a video recording available from this presentation on FPGA toolchains. And I don't know when they're going to publish it because they're pretty slow about that. But if you look it up, maybe it will come out someday. So we'll see all the details. So let me plug this thing on. Mm-hmm. Yep. Do what? But of course, yeah. Actually, I think I might just show some MyGen code instead, because this version of the device has a bug which prevents startup until in certain temperatures and other parameters. And I think we have just hit the right spot where it doesn't work. This is fixed in the next version of the PCB, of course, but I can turn it on. It is working now. So this is one of the, this bug that you have just seen took us 2 months to fix. It was very frustrating. Sometimes it just didn't turn on. It was just some problem with the flash signals, which prevented the FPGA from reading the flash at startup at some point. But just a lot of pain to fix little details like that in the design. So that is actually running on the FPGA. All the video signal is generated in the FPGA. I can even show some settings that will be converted to CPU and everything. So let's see if the camera is working. Yeah, it is. So that's a little camera. And that's one of the effects you can do using the camera as source. So this is processed live on the FPGA. So you have a lot of possibility of interaction. I'm not going to show them today because I don't have time. But if you connect a MIDI controller on it with sliders and stuff, you can tune the zoom or add borders or change colors or do lots of things. Yeah. Sorry? Yeah. Yeah. So actually, what I have just shown is just written by made by these 7 lines of code that you see here. Yeah. Yeah. And if you connect a USB keyboard to the Milkymist, you can edit this code here. So you can make your own. You can make your own very easily, or you can just download them from the internet and connect them and transfer them to FTP. Yeah, yeah. These are just various parameters for the video. What else? Yeah, we can interact with sound as well. I'm not going to show it either, but with sound, we can synchronize that to sound, change the zoom. Yep. No, it's not based on an NVIDIA language. It is based on Mildrop. Mildrop is an audio visualization plugin for Winamp, and that's what we use as a base for this programming language. We don't use any existing Mildrop code now. Yeah, yeah. Actually, a lot of these scripts are imported from Mildrop. Yeah, yeah. I'm looking for another one which I can find now. Yeah. Maybe this one. This one is generative, it doesn't use the camera. And it reacts to sound, so when I'm tapping a little bit on the box, it's gone. Yeah, you can just edit this code and you can change lots of parameters from there. I'm looking for another one with a camera, but I can't find it. This is. Yeah, that's another one using the camera and putting some pretty heavy distortion on it. What?
40 by 40 VGA.
Yep. Yeah. But if you want to take the user interface, you can switch it to higher resolution if you want.
Oh, it's an actual 40 by 40.
Yeah, yeah. I think it does. Yeah. But that's only for the user interface. When you are rendering something, it switches back to VGA resolution, because we don't have enough memory bandwidth to do this resolution in rendering now. But it's basically a problem of the memory controller. We can clock the DRAM higher, and we can have a more efficient access pattern to the memory by using transaction reordering, and that's what we are going to do with the next version of the system on chip. And then you will be able to do this resolution and then maybe even more. Sorry? Our own. Yeah, of course. I mean, what else?
I didn't know what had it.
Actually, open cores as an Ethernet MAC which works, which is rare enough to be mentioned, but it just works. I mean, but it's pretty bloated and uses. It's actually bigger than LM42. So you have the Ethernet MAC from open cores is bigger than our CPU.
And then who's buying it?
Michael.
Oh,
Michael, yeah. Okay, so I think it's time. Thank you for your attention.
That's it there?
Yep.
Pretty neat.
Yep.
Does it have like microphones in there?
It's inside, yeah.